Hello. Today I would like to talk to you about something that's very, very difficult for university faculty, something that can pretty much only be done outside of university, and that's transitioning your innovation from lab to prototype to product. It's the ugly middle of innovation. It is the so-called valley of death, or it's where most technologies, no matter how awesome, it's where they struggle. It's transition from a very cool idea or maybe mathematical model into a smoking, screaming engine. We'll talk about moving from concepts to real hardware, engineering versus theory, and as a bonus, at the end of this video, I'll show my huge, gigantic, big failure. That one hurt, but we'll talk about that in a bit. So hello, my name is Greg Fridman. I have a PhD in bioengineering. I stayed on after that as faculty for over a decade at university and failed transitioning commercializing plasma systems from within the university, so left to run it full-time at my company where we are focused on atmospheric pressure and non-equilibrium plasma systems and trying to commercialize them in medicine, environmental remediation, destruction of forever chemicals, and other amazing applications. So let's talk about the idea stage. Regardless, whether you're undergrad student, not even a student at all, or you're 30-year tenure faculty, there's the idea stage. Theory is beautiful. Initial lab testing data, amazing. High purity, small scale lab bench experiments where you take Sigma Aldrich ingredients of ultra-high traceable purity, react them, and get an amazing result in a controlled lab environment. I called it early optimism. It's the idea stage. You know, I consider many people my mentors, even just the ones whose books I read or podcasts I listen to. So one of my mentors on a podcast mentioned that any idea, it's not $1 million idea. It's a minus $5 million idea. It's going to take you, regardless of how simple the idea is, it's going to take you millions in funding to actually transition it from amazing lab data into the actual customer's hands. That's a big effort. Trust me, been there. So you get your first pre-prototype. You have to think about scaling. That introduces complexity. You built one, it took you a month. The second one is going to take 2 days? Maybe. How about 1,000 of them? You know, scaling is tricky. There are logistical limitations, like maybe some parts you need are from Canada and there are new tariffs. Did you account for that in your pricing structure? Hardware limitations start to pop in. Maybe the part you used for your initial prototype isn't really designed for a field environment. Like lately I've been tinkering with Arduino. And Arduino breadboards, they're beautiful for, a lab testing bench, but then transitioning from that breadboard into a mass production type environment, it can get tricky. I'm not saying it's not possible. It's very possible. Many, many people are doing it. I'm just saying you need to think about that. Power delivery to your system, materials constraints. Is a child going to hold it and chew on it? Because, well, if it's in someone's home, that's quite likely to happen. We have 2 cats and a dog. And these guys chew on anything they can get their paws on. And of course, things never work as expected. As you're moving from the lab, where your experienced technician or your experienced coworker can quickly fix anything so quickly you didn't even notice it was broken. When you start moving into real environment, things change. That's when we hit engineering reality. Did you think about thermal management? In a lab, thing never got hot. Well, that's because you never ran it for more than 10 minutes. What about if I forget and leave it plugged in overnight? Is it going to set my house on fire? There are challenges, especially with power electronics, and the more power, the bigger the challenge is. I'm terrified of any kind of prototype. Unplug it when I'm not watching it like a hawk. Things have caught on fire in the past. Thank God, no one has ever gotten hurt. Knock on wood. There are mass transfer limitations. There's mechanical robustness. Like, you have to think as you're moving into engineering reality. There are all these constraints that you never think about when prototyping. What are the failure modes of your device? Let's say it has metal parts, and I'm in Ohio, it's dry, it's winter, I'm wearing things that seem to constantly generate static as I walk on carpets. So what if there is a spark, an arc, between me and your prototype? How is it going to handle that? Or is it just going to explode? How do your components do in the sun? These windows don't have UV protection on them. So what if I leave your prototype or your device next to the window? How quickly is it going to discolor? What's it going to look like when it discolors? What are your measurement uncertainties? You're testing everything. You're making sure that you're at least 2x below the breaking point. How certain are you that your measurement devices are actually showing you what they should? And as your device runs, are there any unintended chemical byproducts? Like, is it going to generate poisonous gases? There was a big failure in the industry of plasma sterilization right as I was beginning my career. There was a company that was producing plasma-based medical device sterilizers, and they worked beautifully. Equipment got sterilized, bugs were killed, but when these systems were deployed into the wild, turns out there's a pair, I believe it was a pair of scissors, like surgical scissors, that were welded at one point. And when you put that weld, scissors with that weld, into this plasma sterilizer, the plasma, specifically peroxides, interacted with the weld and made it carcinogenic. So the scissors became carcinogenic after the sterilization. Now, this was a couple of decades ago, and those scissors are no longer used. The weld technique is no longer used, but plasma sterilization still has a bad rap because of that one unintended chemical byproduct that was never considered. It should have been. There is no limit to perfection of validation and finding all of your failure modes, especially when you're dealing with human lives, like the medical device sterilizers. And of course, there's the funding gap. Where are you going to get money for all this validation? Like, even your investors are telling you, look, your prototype looks beautiful. You tested it against a dozen different metals, and you cry out, well, we didn't test all of the possible welds, but the investors are saying, go, go, go. What are you going to do there? You heard of technology readiness level? This NASA scale is 9 technology readiness levels, TRLs, going from 1 being basic idea to 9, it's flying in space. And as you transition from one to the other, there are all these, funding requirements drastically changed. It's very different, the costs of testing a low TRL idea, or maybe you want to run some validation on a lab bench, to a TRL 789 idea where that little quick test must be done in deep vacuum and space. Costs of those validation experiments differ quite a bit, and so do the timelines. Like, for example, we went from Democratic to Republican president transition, and a lot of funding goals and requirements and challenges, they all changed almost overnight. So how does that affect your timelines? And when the in-between presidents is approaching, you should think about that too. So what are the long-term budget constraints, and what's the level of accountability for your deliverable, which is often a major question with federally funded, like, for example, SBIR projects. You need to iterate your designs. I suggest having some logical, structured testing plan, data-driven designs. You need to have a kill criteria. When do you declare? What are the specific requirements to declare your idea bad? And of course, you need to do that with all of that. You need to do with a bit of engineering humility. Your idea feels like the next best thing since sliced bread. Is it? Humble yourself. I'll tell you about my tractor, which was the best thing in the world. Nah, it wasn't. Turns out it wasn't. Anyway, there is something called systems thinking. No matter how large or small your product is, it integrates into subsystems. Like if you design a new laptop, well, it's going to be plugged into stuff, connected to stuff, placed on stuff spilled on it. What happens in those situations? Like what happens if somebody spills acid on your laptop? And don't say that never happens. In a farm setting, peracetic acid is everywhere. So if your product is used in a farm, how are you going to protect it, or at least inform users where they should be careful? Speaking of user interface considerations, how big are their fingers? Who is this being designed for? And what are the requirements of the user interface or user interacting with your product? And speaking of, what are the regulatory constraints? What agencies even regulate your product and everything surrounding it? There is Center for Disease Control, CDC. There is Food and Drug Administration. There is USDA, EPA, FDA, all sorts of regulatory agencies. And don't forget about ITAR, International Treaty in Arms Regulation, or something like that. That applies to any kind of system that could have some military relevance or somehow be connected with our nation's security. And, as you think about the systems, what are the realities of field deployment of your device? So you always have to consider that as well. And back to scaling challenges, energy efficiency becomes quite important. If your device runs on a battery, how long does it run on a battery? There's a light shining at me over there and over there and over there. Those are on batteries. And if that battery runs out in 5 minutes, well, it's useless, no matter how elegant, beautiful, or amazing it is. What is the cost per? Maybe, well, there's the CAPEX and OPEX, capital expense and operating expense. So what is my total cost of getting your sandwich maker to make me one sandwich? And if it's 100x of going to get a sandwich from a grocery store, maybe I'll just go and do that instead. The reliability of your device. So CAPEX, capital expense, but over how long? You have to consider reliability over time, both of your device and the requirements surrounding that. Like if you're designing a system to go into a municipal water utility plant, well, they don't change very often. They usually run 10, 20, 30-year repair cycles. So your thing needs to run virtually unattended for decades. It's funny, a friend of mine is in petrochemical industry, and we were talking about flame sensors. And, my dumb question, don't they have flame sensors? And he says, well, yeah, they do, but nobody uses them. Huh? Because they break after a couple of years, and nobody wants to replace them for the 20-year lifetime of the burner. So for first couple of years, flame sensor works, and then it breaks. Yeah, I know it's harsh environment, but that's what we're talking about here. And, oh, by the way, how manufacturable is it? Can you easily switch from sourcing your parts in China to sourcing them in Vietnam, or just building everything in continental USA? Some items, especially microelectronics, and we're having shortages of all sorts of microelectronics. Good luck buying RAM for your new computer. I mean, don't even get me started. So manufacturability challenges are also something you need to think about, and not just for tomorrow when you're making first batch of your devices, but also for 10 years from now, assuming you're successful and the manufacturing continues. Can we still make it the same way in 10 years as we're making it today? And as you're doing all of this work, you need to keep an eye on when to pivot. Recognize diminishing returns, get market feedback as early and as much as you can. Get early adapters, get all of their feedback you can, so you can pivot. What are your technical dead ends? Make sure that as you're developing a product, you remain cognizant of what a dead end is. What's that going to look like? What is strategic redirection? What are you going to do when you realize that you might be at a dead end of the branch that you were traveling on? Can you pivot to something? What's your strategy there? So I've been doom and gloom. What products actually succeed? I'll let you know when I get one. But the ones that we got close to success, they had very clear problem that they're addressing. Clarity in problem definition ensures you're on the way to productization success. Is it a problem? Can you define it in one sentence? Can you define it in one word? What are your milestones? Are they measurable? They have to be measurable. Otherwise, how do you know you're on the right track? Your team, obviously, needs to be strongly interdisciplinary. You need to have USDA experts if you're working in the USDA domain. You also need material scientists who understand how environment interacts with what you're trying to design, etc., etc., etc. And what succeeds? Relentless iteration. Keep iterating until you arrive with the absolute best version of your product. So finally, let's talk about my failed tractor. So we built this massive, expensive attachment to a tractor. Here, let me show you a video. This thing spans 30 feet, covering 5 beds of spinach, with 25 plasma fogging units hanging off its back. Our control experiment is loading the same thing without plasma and adding oxidate instead of water. Oxidate is a mixture of hydrogen peroxide with peracetic acid. So we did almost 10% better than oxidate. Hallelujah. Everybody was jumping up and down. We ran our plasma tractor up against the best of the best. Oxidate is the grass generally regarded as safe pesticide, and plasma did a little bit better than the best. And that's before we even started to try to optimize it. What happened? We went to investors. A bunch of eager engineers. Look, we got it to work. It worked in a lab, in a petri dish. We can kill bacteria. We can kill bacteria on spinach leaves in a lab. We can kill bacteria on one spinach plant in the field. We can put it on a freaking tractor and kill 30-foot span of bacteria on spinach in the field, moving at 4 miles an hour. And we outperformed Oxidate. Well, it is an engineeringly complex system to design. It's high voltage. It's high voltage next to farm workers, which are amazing, excellent people, but very few of them are PhDs in plasma chemistry. There are fears related to equipment malfunction, difficulty to repair these systems, CAPEX, capital expense. It's funny. When you look at CAPEX and OPEX for plasma and Oxidate costs pretty much exactly as much as the diesel fuel that our power generator for plasma uses. So operating expense for Oxidate and for plasma, same. Capital expense for plasma is about triple. So it's approximately $60,000 as cost of goods sold to put that system on a tractor. It's much cheaper to put Oxidate on, about 3 times cheaper. So there is the CAPEX challenge, but what works for us is we don't have the logistics tail. So Oxidate, it has short expiration time, so you need to make sure that your logistics people constantly deliver that to your field. But maintenance requirements, manufacturability requirements, everything I talked about in today's chat, all of those problems are things that when we dug into them, we realized that we don't have a product. Because even if we built it, the number of customers is not enough to recoup the cost. So we continue to use Oxidate until, for some reason or another, we'll come back to plasma technology. So all of the groundwork is done. Now we just need to commercialize it. So with that, some closing thoughts. There are plenty of amazing ideas, but true innovation lurks in this uncomfortable, murky middle. That's where most ideas die slow and painful death, taking with them years of your life, like what it did with me. But it's okay. I got to ride a freaking plasma tractor. How many of you can say that? Anyway, your prototypes are important. They expose reality. I never thought, in hindsight, I should have, but I never thought about that guy who's going to have to maintain plasma tractor. I never considered his safety and what I would do to protect them from almost inevitable electric shocks with malfunctioning high voltage equipment. I don't want it to malfunction, but it's a tractor in a field. Forget all the shaking. What about it bumped into a tree and broke half of the wing off? That you're gonna have to repair. True engineers, we stand up to these challenges. That's what it's all about. So with that, let me know down in the comment section what we should talk about next. I'm always excited to get your questions. I think about them, and the ones I can respond to, I make videos about. Peace, y'all. See you in the next one.